is to pursue a little bit the consequences of this kind of spin-orbit non-separability, okay? We will start by looking to somewhat surprising property of this kind of classical non-separability, which is the role played by formally equivalent the role played by inequalities that are formally equivalent to quantum inequalities such as the Bell inequalities to determine whether a quantum state of a pair of qubits is entangled or not, okay? And then I will illustrate how how structured light and this kind of structural non-separability between spin and orbital degrees of freedom can be used for quantum communications, and describe the kind of protocol that we are going to use in the Rio de Janeiro quantum network, okay? So first, let's discuss about this issue of spin-orbit Bell inequality. So during the last lecture, we introduced these structures here that are combined polarization and spatial mode structures that cannot be factorized. So we could also physically interpret them as beams or field configurations in which the polarization state is not uniform over the wavefront, okay? But it varies along the beam transverse plane, okay? So these are non-separable structures, even in classical optics, okay? Even in classical optics, they are non-separable structures. Now, is there any role for an inequality such as Bell inequality in this context? Can we translate also? We have translated some aspects of the mathematical description of a two-qubit system, but now the question is there a role for the well-known Bell inequality for a pair of qubits? So the answer is yes. So the idea of the Bell inequality, I will just briefly mention that, is that, for example, you measure the properties of two spatially separated particles, okay? For example, spin-half particles or two photons with their polarizations, okay? Individual polarizations, and you make measurements in a different set of bases, and what you get is you get an amount of correlation that can be measured, okay? And this amount of correlations measured for different settings of the measurement apparatus can reveal correlations that cannot be explained by assuming classical statistical models for the variables being measured, okay? So it excludes local statistical models based on classical probabilities, okay? The only way to explain these kind of correlations with classical probabilities would be to have some kind of non-local influence, something that non-locally influences the measurements in both sides, okay? However, this is, of course, this can also be ruled out by the so-called the loophole, the relativistic loophole. So if you just put the two measurement sites apart and make the measurements at intervals that cannot be connected even by a light signal, then you are sure that the two measurements cannot affect each other. So this is one main role. The Bell inequality was conceived to rule out classical statistical models for remote measurements in parallel particles, okay? However, this is not the only role of Bell inequalities in quantum theory. So Bell inequalities, the quantity that is evaluated in the Bell inequality, this S quantity here, that is related to the statistics. It combines the statistics, the correlations measured with different measurement settings. Okay, this quantity here can also be used as a witness, an entanglement witness. So at this point, we see two roles for Bell inequalities: the role of ruling out classical statistical models for remote measurements, okay? But it has also this role of serving as an entanglement witness for a pair of qubits. And this has nothing to do with non-locality or whatever. It's just a mathematical property, okay? So we start to, as we did in the last lecture, we will make a formal equivalence between the objects that figure in the Bell inequalities and the objects that appear in this classical optical description of spatial modes and polarization modes, okay? So essentially, you have a given field configuration that can be written as a superposition of all possible combination of first-order spatial mode, okay, Hermite-Gaussian horizontal or vertical, and linear polarization unit vectors, horizontal and vertical, okay? We can also define the rotated basis, so we can think of a change of basis in each degree of freedom, both the polarization and the spatial mode. These change of basis can be made by wave plates in the experiment, okay, and by Dove prism for the spatial mode, okay. Now, we saw that this kind of interferometer sorts out the two different kinds of modes, of spin orbit modes. It goes with HH and VV from one side and HV and VH to the other side, okay? So it makes a kind of joint, if we encode two spins, one spin on the polarization and one spin on the spatial mode, first order spatial mode, we can think that this interferometer here makes a collective measurement. It measures the product of the two spins, if you want, okay? So positive product goes to one port, negative product goes to the other port. If I precede this interferometer with the devices that I need to rotate both the polarization and independently the spatial mode, then I can have different settings for the measurement apparatus for different bases, the basis projection, okay? So the angles theta, phi and theta for the Dove prism and for the wave plate are equivalent to the spin analyzers or polarization analyzers orientations of the two remote detections at the Bell inequality setting, the usual Bell inequality measurement setting, okay? But here, we don't care about non-locality. We don't want to rule out. We are not worried about ruling out any classical statistical. We are not doing any statistics here at all, okay? So the point is that the measurement intensities in these two detectors here, they are calculated in the very same way that we calculate probabilities in quantum theory, okay? So, but these are just classical intensities, intensity of a classical beam, okay? So, and I call these the projected intensities because it is, you obtain the intensities in each detector from the original structure by calculating this quantity here, which is equivalent to projecting the quantum state of a combined two qubit system in a given product state basis, okay? So you first do the usual dot product with the unit vector, and then you make the formal dot product for square integrable functions, and then you obtain the projected intensities. So these projected intensities, they play the same role as the probabilities in the quantum theory, okay? Now, what is interesting is that you can do this, all the calculation analytically, and what you see is that if the original structure cannot be factorized, okay? If the original structure can be factorized as a product of an arbitrary spatial function with an arbitrary polarization mode, then this quantity S will be less than 2. The quantity S that I build with the projected intensities, okay, will be less than 2. If the quantity S surpasses the value 2, then you are sure that there is some kind of non-separability between the spatial part and the polarization part. Note, this quantity S is an entanglement witness, but it's not an optimal witness, okay? So violation of this inequality is sufficient to guarantee that you have a non-separable structure. However, non-violation doesn't mean that you have that you don't have a non-separable function, okay? So in this case, what is interesting here is that we could use this quantity even if you have in your lab large detectors, okay, bucket detectors that swallow the whole beam, and you are not sensitive to the detailed spatial features of the mode, you can evidence that there is some kind of spin and orbital non-separability by calculating this kind of inequality. And there is a formal equivalence. The physics behind this is completely different, okay? This is why I insist on the point that the difference between classical and quantum theory does not rely on mathematical constructions only. It relies essentially on the physics of the measurement and the interpretation of the measurement results. There, at the measurement level, there are the differences between classical and quantum, the most striking difference between classical and quantum theory, okay? So here, the measurements are completely different. So this is how the experiment looked like. So we did this experiment back in 2010. We had a very big, it was really a big issue because we were talking about Bell inequality in a classical domain, and there was a very, very strong reaction against that in the beginning, okay? Notably from the people in quantum information theory, okay, which unfortunately at that time these people did not have the skills for optics. You know, optics is a very, very rich domain in which you can realize many beautiful mathematical structures in it, you know. So it's a very rich domain. And this is one example. At that time, we had a long problem. This paper took like 1 year to get published, okay? Like 1 year by fighting with the referees and so on. And they only accepted the paper, the referees, when there was a referee that said, okay, so these guys, after all, actually their system is entangled. It's quantum mechanical entangled, and they are just showing quantum entangled, Bell inequality violation in one more entangled system. So it's not new, it's not interesting. And then what we did was to actually quantize all the modes in the problem and show that a product of coherent states in the input modes also give the same violation. And this was done theoretically, analytically. We told the referee. So you check the calculation and you tell me where it's wrong. Okay? Then the paper got published. But it took us like 1 year, more than 1 year. Later, we repeated the experiment, but we got higher violation, and we also could extend not only to 2 degrees of freedom, but we added the path, the longitudinal path, as a third degree of freedom, and we also demonstrated violations that are quantum mechanically formulated for 3-qubit system, like Merlin inequality or something like that. Okay. Now, in arguing with the referees, we had to somehow put quantum theory. Okay, so if we keep like arguing using only classical theory all the time, it's difficult to talk to people that are quantum opticians or quantum information people. So let's go and make all the theory, all the quantized theory as it should be, okay? So let's start with the quantized vector modes. So here, I'm talking about quantization of the electromagnetic field, okay? So it's not a single particle or a well-defined number of particle system. The electromagnetic field is quantized, the field is quantized with the language of second quantization for those who have learned the second quantization in many-body physics, okay? So why is that? Because in many experiments, in most experiments, you are not sure about the number of excitations you have in the experiment. Okay, so when we talk about a coherent state in quantum optics, for example, a coherent state does not have a well-defined number of photons in the modes involved. So the constructions that are very common in quantum information, so I have n qubits. N is well-defined. Well, if I'm sure my experiment has 2 photons, 4 photons, or a given number of photons, you can treat the photons as individual particles that they and talk about like correlations between them and so on. But if your apparatus does not have a well-defined number of photons, okay, you have a superposition of having 0 photons, 1 photon, 2 photons, 3 photons, then this no longer works. How do you do the usual quantum information theory if you do not know how many particles or how many qubits you have in it's more than that. You know, the number of particles is itself a quantum operator. So we are dealing with a different theoretical context. So the main point here is you have a given configuration of the electromagnetic field. So if we take this positive frequency part, so we can expand this configuration of the quantum electromagnetic field in terms of the modes. Remember, the mode structures are the same. Quantum theory or classical theory, the modes are the same. The difference are the amplitudes that you put in the mode, because the amplitudes in quantum theory, they are quantized. They are quantum variables, okay? They are described by operators that do not commute or satisfy a certain commutation rules and so on. Now, I can do this expansion in terms of the vector vortex or the non-separable mode structures that I mentioned, or I can do the same kind of expansion, but now using the factorized spin-orbit modes. So here are annihilation operators defined in this mode structure, and these are annihilation operators defined in this mode structure. However, you have a mapping, a transformation map between one mode structure and the other. So this is how you define these modes, in terms of these modes, okay? These 2 equations give you that. Well, if the 2 expansions they describe the same physical object, the electromagnetic field, the electric field in this case, then the annihilation and also the creation operators must be related in one basis set and the other basis set, okay? So what happened is that we can use the creation operator as our tool for building states. So I know that from the vacuum state or for the electromagnetic field, I can build any state by applying the creation operator, okay, or combining powers of the creation operator. I can build any state of the electromagnetic field. So let's build, for example, a Fock state. So one Fock state, suppose I have one state in which, I have one photon at mode HH, horizontal polarization, horizontal emit Gauss. 0 photon VV. So I act this A dagger here, HH, on the vacuum, I obtain this. Or I can add one photon here. However, you see, what happens if I create one photon in the vector mode and one photon in the radially polarized mode, like this one here? So I act the corresponding creation operator on the vacuum, and then I obtain one photon here, 0 photon in the other one, which is orthogonal. Note that, you see, these, I'm only using HHVV for the factorized modes, and psi plus and minus for the non-factorized modes, because they obey a close relation, okay? So I only need those two to obtain this, and I only need those two to obtain any one of those, okay? So I suppose that all these guys here are at zero photons, okay? I don't care about them. Now, if I produce one photon at psi plus, what I see is that in the same translation to the HHVV modes, I have an entangled state, okay? So I have a photon so the two modes, this is mode entanglement, okay? You have only one particle, only one photon, but you have two modes. In either decomposition, if you are in the vector mode decomposition, you have psi plus and psi minus. In the factorized decomposition, you have HH and VV. So the two modes are entangled, okay? There is no point in talking about entanglement between photons because you have only one, all right? But the modes are entangled. So this is the entangled state of the two modes. Now, if you have two photons in your apparatus, so one psi plus and one psi minus, then you act the creation operator, and now, again, you have an entangled state here. Now, it makes sense in talking about entanglement between the two photons, okay? They are both, the two photons, either the two photons have both horizontal polarization and horizontal emit Gauss, or they have both vertical polarization and vertical emit Gauss. This resembles the theory of Hongu-Mandel correlation, okay, in which you have one photon at each input of a beam splitter, and at in the two output modes, they are in a state like that. Two from one side, 0 the other, or the other way around, okay, with this minus sign. So it's very similar. The mathematics is the same. You have a question? You see, this is why I stress the point that modes are common structures for both quantum and classical theory. So in quantum theory, you have the modes. The modes, they are wave-like structures, always. We had this discussion yesterday, or the day before, I don't remember. But modes, they are wave-like structures. And the quantization has the consequence of saying that you have you can only occupy these modes with discrete values of energy. but they are always spatially distributed structures, okay? So the question that you are having, that you have now, is related because you have a bias towards thinking of the photon as particles, as small balls, and that somehow the electromagnetic field is a wave function or a amplitude probability or so on, okay? So it's not, well, I would say this is not, I don't like this kind of, you can think like this, in this way. It works whenever you have a definite number of photons in your apparatus. But if you don't know how many photons you have, then it breaks down. However, the wave-like picture in which you treat the modes as wave structures that are always there and quantize their amplitudes, this you can use always, okay? As long as quantum electrodynamics works, okay? As far as the theory works, you can use that interpretation.
So you're only saying that, for example, in that first equation, you're only saying that the horizontal Hermitian mode has quantum of energy.
A quantum of energy. I have h bar omega energy in that mode. That's the best you can say about this, okay? Now comes the problem when you don't have a well-defined number of particles or of excitations in your modes. So what happens if I try to, if I build a coherent state, and now this is a laser, I can model the laser like that, okay? A laser that I just passed through some modulator and polarization and spatial modulator that prepared a beam that is mid-Gaussian, horizontal, with horizontal polarization, okay? Then, in this case, you have this kind of state. And you can obtain now, the machine, the mathematical machine for building a coherent state is the displacement operator. So I take the displacement operator, act on the vacuum, okay? Act on the vacuum, and I obtain this state here. I can apply the other displacement operator, VV, and build this other state here, okay? Now, the point is that these operator and this one do not commute. There's a H bar, A and A dagger, they don't commute for the same mode, but they commute for different modes. This one and this one commute, this one and this one commute. So actually, if I do the same, now I'm going to build a coherent state in the vector vortex mode. So a coherent state, this is what I obtain in the lab if I take a laser and pass it through some S-plate or whatever to generate the vector mode, okay? Then the coherent state in this mode here, since these operators, they commute, can be factorized as in this way. So a coherent state in the psi plus mode is a product of coherent states in each one of the composing modes, H, and VV. It's a product of coherent states. So there is a striking difference. Here, these Fock states, they are entangled states of the modes H, and VV. But the coherent states, they are separable in, it's an order. So people usually say that coherent states, they are classical-like. And they are classical-like because of the behavior of the average value of the electric field that oscillates with time. But they are also classical in this way, because if you have an electromagnetic field that you prepared in some given coherent state, it will be a coherent state in any kind of mode decomposition that you do. Okay, it will be a product state in any kind of mode decomposition that you do. It does not change into depending on the mode decomposition, does not change into entangled one. Now, of course, maybe someone may think about, entanglement does not depend on the basis. This is true. Entanglement is insensitive to local change of basis, but not to global change of basis. The change of mode structure in this case is not a local. Okay, it's not local in the sense that it's not, it does not involve an independent transformation in one mode, in one degree of freedom, and on the other degree of freedom. So you mix them up. So this would be the equivalent of, for 2 qubits, making bases that involve the two, how can I say, the 2 qubits together, not only a factorized unitary transformation on each side. Now, again, if we revisit, so this is how we had to deal with the referees at the time. If we revisit the measurement of our measurement apparatus, okay, now we have the interferometer, we have the transformation devices here to change the bases, we have an initial state, which is like a given quantum state prepared in the vector mode, okay, 0 on the orthogonal 1. Here we have vacuum coming in. You have if you are doing quantum theory of this interferometer, there is always something coming in all ports, all input ports. When you say nothing, nothing means vacuum, okay? And vacuum means noise. So what happens is that now we compute analytically, okay, the S value, the expected S value from intensities, which now the intensities, they are calculated like that. They are the average of the B dagger B, for example, for the annihilation, the number operator for each mode involved in the inequality, okay? And what we get is that if I have one single photon in psi plus, then it's an entangled photon between HH and VV, you obtain 2 square root of 2, the maximum possible value for the S quantity that is defined in the Bell inequality. Now, if you plug into this the coherent state, now a coherent state here, okay, which is a product state of HH and VV, and you calculate the same quantity, it also gives you 2 square root of 2. Okay? So we showed this calculation, and we told the reviewer, do it yourself if you want. Okay? It's very, very easy. Of course, we can talk about partial entanglement. What happens if I have, for example, a state that is, for example, if I have a number state in a given mode with a larger number of photons, okay, when I decompose the modes like the vector mode, the radially polarized mode in terms of HH and VV, I have this kind of state, which is not factorized, okay, it's entangled. Of course, you have always 2 square root of 2, okay? Now, if you have a statistical mixture, now what I did here, I considered a statistical mixture, a state of a statistical mixture that has the same photon probability as the coherent state here. And you also get 2 square root of 2, okay? And if you do some kind of Werner state in which you put some weight P for this mode here, and you put 1 minus P for the statistical mixture, then you can interpolate between square root of 2 and 2 square root of 2, okay? Another point that we did also was to consider a partially coherent mode, okay? So suppose I do this. So this is starting from a laser that is horizontally polarized and prepared in a horizontal emit Gauss mode, I can get, for example, some, how can I say, some non-separable mode by doing this, okay? However, what we do is we contaminate this, this mode structure with an independent laser that does not have this a well-defined phase relation to the first one, okay? So what we get here is something that is a combination of a coherent state with HH, okay, and some statistical mixture of coherent states at VV. And this statistical mixture is because we are contaminating the signal with an independent laser that does not have a well-defined phase relationship to the first one. Okay? So at this point, we can compute again the S quantity, and we see that we can interpolate between square root of 2 and 2 square root of 2. So this, somehow we relate the violation of the quantity 2 square of the S bound 2 to the coherence of the mode produced in this case, okay, of the vector mode that we are producing. Now, this kind of spin orbit analogy, this kind of quantum classical analogy, we have like explored this in our lab, not a little bit to show that we can do things, we can profit from quantum information concepts, even in this classical optical context, okay? But also because it allows us to do some how can I say, operations that even classically are not very easy to do, to be done, okay? So, for example, consider this, this problem, okay? Now, remember what we did, we talked about quantum teleportation, so the idea, this is just the sketch of the protocol. You have a given, Alice has a given state, an arbitrary state, alpha 0 plus beta 1, okay? She shares an entangled state, maximal entangled state with Bob of 2 qubits, one in her possession, one in Bob's possession, okay? And now the idea is that Alice makes a Bell measurement between the 2 qubits that are in her possession and the coefficients that appear in this state here are transferred to Bob's qubit, okay? Apart from a unitary transformation. So then, what we did, there was a problem that we had in our lab. Was, okay, I want to prepare an arbitrary, because when we started all this structured light investigation, we didn't have money to buy a spatial light modulator. So then we started to argue, I want to make an arbitrary superposition of horizontal and vertical Hermite Gauss modes. How can I do that if I don't have a spatial light modulator? I only had at that time in the lab polarizers, polarizing beam splitters, and wave plates. So I could prepare arbitrary polarization states, but not arbitrary spatial modes. And then there was this idea, so let's try to use a third degree of freedom and try to mimic the teleportation protocol to prepare arbitrary polarization modes and transfer the information, the coefficients, to the spatial part. So what we did, so this is how it works, okay? So we had 3 degrees of freedom. One was the polarization, where we encoded the arbitrary superposition that we wanted, okay? This would be the equivalent to Alice A qubit, okay? Then we used the second Alice qubit as the path, and the third one, the Bob's qubit, as a transverse mode, okay? So the transverse mode are supposed to receive the polarization coefficients that I have, okay? So I change this. So this is qubit A, the analogous to qubit A would be the longitudinal mode, okay? So just the path. Qubit B are the transverse modes, psi plus and psi minus, here in Laguerre-Gauss basis, and the intermediate, the C was the polarization, okay? So input, we want this as input and this as output. So we want the polarization superposition to be transferred to the spatial mode superposition. So this is how the experiment looks like. Here I have one path where I prepare an arbitrary polarization state, okay? It goes into an interferometer. In one interferometer, I do some what we call here, this path transverse mode non-separability. So this guy switches, it flips the transverse mode. This one flips the polarization. And then what happens here is that in this side, the spin orbit mode is orthogonal to the spin orbit mode at that side. And then I mix them up at the output beam splitter, and I have two PBS, two polarizers, so I make the measurement. So this is a joint measurement between polarization and path, because these detectors only see what's in this path. These detectors only see what's in that path. And each port of the polarizing beam splitter sorts a different, projects into a different polarization mode. So here, I have what is analogous to the Bell measurement. I have the 4 projections that are joint projections in path and polarization. And what happens is that once we do that, okay, we see that the 4 outputs are the 4 quantities, the 4 possible combinations of psi plus and psi minus. So in one port, we will have a alpha plus beta minus, the other one alpha minus beta, and so on. Beta plus alpha and beta minus alpha. So actually, okay, one of the ports, one of the output ports will have exactly the same superposition of the polarization mode that I prepared initially. Okay, so I can have the arbitrary, now I could prepare arbitrary polarization or spatial mode in first order spatial mode, playing only, controlling only in the initial polarization mode that I wanted, okay? This is all classical light. These are images. These are the experimental images, okay? These are the experimental images. These are experimental images. In here, I have the simulation, the calculations, okay? And all these points, 1, 2, 3, 4, and so on, are points on the Poincare sphere. Okay, so these are points on the Poincare sphere. These are points for the Poincare sphere, the sphere for polarization, and also the sphere, the sphere for the input polarization, and also the sphere for the output spatial mode. Okay. There is just a detail in this mapping, is that actually for the polarization we put on the poles the horizontal and vertical linear polarizations. But for spatial mode, we put Laguerre plus and Laguerre minus. This is just an encoding. That is not very important here, okay? So with that, we could transfer, we could prepare. So this was the poor man's solution. Without the spatial light modulator, we could have the spatial superposition that we wanted, right? So not having money is sometimes is a good thing for science, okay? Now, spin orbit also, something that we did was like, we could also, for example, do a version of a stigmatic. What happens here is that the stigmatic mode converter, it was also used for the same, with the same objective, okay, to prepare arbitrary spatial modes, okay, without spatial light modulator. So you have, we know that the stigmatic mode converter does this, okay? And I talked that this transformation is done with the GUI phase inside the astigmatic telescope, okay? Now, what happens is that actually if you look at the evolution of the wavefront inside the telescope, we see that in this symmetry plane, the wavefront becomes plane, okay? So you have a curved wavefront. After the cylindrical lens, the curvature in one direction becomes different from the curvature in the other direction, okay? But this curvature evolves with the propagation, and at the focal plane, it becomes plane. And then it changes again to, it inverts the sign of the curvature, okay? It changes the curvature. So it's a bit like that, okay? And with different radius in one direction and on the other direction because of the cylindrical lens. So we decided, well, if the wavefront here is plane, then I can get rid of this part and put a flat mirror here. A flat mirror is the most common ingredient in any lab. And make the whole transformation with just one lens. I could do better than this. I could do a pi transformation, and which is conditioned to the polarization. So instead of doing just this was just to make the transformation. So the beam comes horizontally polarized with arbitrary spatial mode. Since it is horizontally polarized, it is transmitted. It passes through a quarter wave plate that turns it into circular. It goes, it undergoes the spatial transformation. It goes back, pass through the quarter wave plate again. This makes a half wave plate. So the circular becomes vertical, and when it comes here, it is reflected. So without any loss, we could do the transformation with a single lens, okay? And it's of much easier alignment and so on. Now, we could do better. We could also use this part here, and in this part, if the mode has some vertical polarization component, it would be reflected, and in this arm, it does nothing. So it is a C0 gate. So it comes here. If it's H, it goes there, get the mode, spatial mode flipped, okay? If it's V, it comes here, it doesn't change the spatial mode. So it was a C0 gate in which the polarization controls the spatial mode, okay? And it's very compact, very easy, and very robust, okay? It's not very sensitive to vibration. It's very, very efficient as a gate, as an internal gate. So we are implementing a gate, okay, a unitary gate, in 2 qubits of a single photon, if you want. Now, I would like to start with the last topic of these lectures, in which I will explain essentially what we are going to do in our quantum real quantum network, okay? Real quantum network, the rede Rio quântica. So let me just recall the architecture of the network. We have the institutions involved are Catholic University, these are their symbol, which are located here at the district of Rio de Janeiro called Gávea, okay? We have the Brazilian Center for Physics Research that is located at Urca, okay? So this distance is about 6.7 or a bit less than 7 kilometers in straight line, We have the Military Institute for Engineering, okay? They are also at Urca, and they are just 800 meters apart from CBPF, okay? So it's not very, they're not very far away. We have our university, Fluminense Federal University, which is located like a bit less than 7 kilometers across the entrance of the Guanabara Bay. And we have the Federal University of Rio de Janeiro that is apart from the Catholic University, about a bit less than 14, a bit more than 13 kilometers, okay? This is the Rede Rio. This is the main optical fiber cable that connects the institutions in Rio de Janeiro, okay? So what we see here, you see the Brazilian, there is the cable that connects all these institutions, CBPF, PUC, okay, and the Federal University of Rio de Janeiro. There is a small tail of this backbone that goes to IME, and our university is connected. This is the Rio-Niteroi bridge, okay? There are fibers that go under the bridge, but they are commercial fibers. So for the moment, we don't want to use these fibers to make any kind of communication. We will exploit this link with free space protocols, okay? So this is the view that we have. We have a lab at the top, on the top of our building, okay? And this is a beam that we are sending to CBPF, okay? And this is the sugar loaf. We have a telescope for the alignment, so we can see the lab at the CBPF, okay, through the telescope. There is a telescope on the other side also, okay? We even installed, now we are now making everything is being, how can I say, remotely controlled. So we have automatic control of all the equipment in the lab, and we can the students and the postdoc, they can like access everything far away, okay? And we have a camera over there to see in our cell phone, we can see the lab at CBPF at all times, okay? Now, this is the view. So first, what are we going to do in this free space link, and what does the subject of the core of these lectures have to do with all that? So I will talk about alignment-free quantum cryptography. So this is a work we did a long time ago in collaboration with Stephen Walborn and also with Leandro Aulita at that time in the Federal University of Rio de Janeiro. And actually, the main idea is the following. So let me just recall how the BB84 protocol works. So remember that Alice and Bob, they are equipped with polarizers, okay? So Alice will send Bob photons with randomly chosen polarization among 4 possibilities: age, V, diagonal, anti-diagonal, and Bob will make polarization measurements, and he can set his measurement device to measure in HV basis or in diagonal, anti-diagonal basis, okay? He can choose that. So depending on whether he chose the good basis, I mean the basis that Alice used to encode her photon, okay, then he will get the result with 100% probability. They can trust this state transfer. If he chooses the wrong basis, they have to discard that, okay? So this was how we explained the BB84 protocol. There is a problem with this protocol, okay? The main problem is Alice and Bob, they need to agree with what they call horizontal and vertical. So they need to align their labs. So if there is, for some reason, a small tilt between the 2 labs, the buildings are not well aligned or something like that, okay? Then this introduces errors, okay? So they must exchange information and calibrate the systems to align the labs, okay? If this communication is being performed with a moving station, for example, that rotates or whatever, this can be quite challenging, okay? Now, how can we profit from structured light? I told you that the radially polarized mode and the azimuthally polarized mode, for example, they are two possible orthogonal modes. And look, there are two possible orthogonal modes that are invariant under rotations. You can do this by calculation, okay? It's in the hackathon. But you can also simply look at them, okay? They are visually rotationally invariant. If I rotate this figure, it comes into itself, okay? And it's the same for this one. They are both rotationally invariant, and they are orthogonal. So if instead of using just the polarization, if I combine polarization and orbital part in rotationally invariant structures, I don't need to do this alignment calibration, okay? So they go directly. So this is what we would like to do, we want to do in the free space link, okay? To prepare this kind of vector beams and send from one station to the other, okay? So this is what is being done. We have already tried. For the moment, we have technical problems. We prepared this mode here. We sent to CBPF, but it arrives there with the size of the whole building, okay? Not the whole building, but like at least 2 floors, 1 or 2 floors. So it's very big, okay? We need to work out the optics, okay? But we need big lenses, big mirrors. There is a lot of technical issues to deal with, okay? Now, this is how, okay, the protocol works. So Alice, again, the interesting thing is that these two quantities, these two structures, they are rotationally invariant, but also they are superpositions, okay? So if I combine them with a plus and minus sign, I have then a new mutually unbiased basis to this one, which, since they are, these two are rotationally invariant, these combinations are rotationally invariant also, okay? So then, not only you have two orthogonal states that are rotationally invariant, but you have a mutually unbiased basis that is also rotationally invariant. So Alice and Bob can choose between the 4 possibilities, 0, so the 0 logic, 1 logic, plus logic, minus logic, and Bob must adjust his settings. And how is he going to measure? Well, we know that we have this interferometer that sorts the different modes, and you can precede them, okay, by a C0 gate to change, okay, to change these modes. The C0 gate would like undo this kind of spin orbit non-separability and produce 4 different possible outputs, okay? And he could measure the photons he received, choosing between the 2 bases, okay? And whenever they match the basis preparation and the basis measurement, okay, they can trust the detection made by Bob. There is a success in transferring 1 bit of information, okay? So this was the experimental results we obtained on the table in the lab, okay? So this is, so we have, Bob has 4 outputs, okay? He has 4 detectors, so here are the 4 detectors of Bob, okay? And what we did was we could like rotate their rotate rigidly rotate the two apparatus, okay? The apparatus, the preparation apparatus of Alice and the measurement apparatus of Bob, okay? One with respect to each other. So these are different relative angle orientations, and we see that whenever Alice prepares the photon and Bob's measures at the same, whenever Alice whenever Bob used the same measurement basis as Alice prepared, okay, in his detectors you have one lit and the other one dark. But when they measure in different, okay, bases, so this is Alice, if Alice prepares 0, 1, he measures 0, 1, then in all cases here, independent of their relative orientation, okay, you have one detector lit and one detector dark, okay? Now, if she prepared in the plus or minus, but he's measuring 0, 1, then you have 50% probability, so you have 50% of the beam in each output port, okay? So, and this was the complementary results when Bob, with the Bob's setting at plus and minus, okay? Then these are the cases where you have one detector lit and the other, one camera lit and the other camera dark, the other detector dark, okay? Now, what are we going to do in the quantum, in the fiber optics connections of the quantum Rio network? So the idea here is to use a different degree of freedom, a different photonic degree of freedom. So the, how can I say, the principle is similar to the BB84, but now we are going to encode the bits and the bases in the photon phase, okay? So, and this is called the twin field quantum key distribution protocol. So the idea is the following: the twin field protocol works with three parties, Alice, Bob, and you have an intermediate party, which is called Charlie. And this intermediate part can be, does not need to be trusted. It can be untrusted, okay? It could be the Eve herself, okay? Now, the point is that Charlie sends a photon through an interferometer. The photon here can go one way. It's a Sagnac interferometer, can go one way or the other way, 50% probability. Now, Alice and Bob, they possess phase modulators. They also possess amplitude modulators, but I'm not going to talk right now about amplitude modulation. Let's only focus on the phase modulation part, okay? So what happens is that they can apply in their phase modulation 4 possible phase shifts: 0, pi, pi over 2, 3 pi over 2. So actually, this pair of phase values, 0 and pi, they play the role of a basis. And pi over 2, 3 pi over 2 is a different basis, okay? Also, Bob does the same. He can apply with a phase modulator, he can apply any one of these 4 values here, okay? So what they do, they apply their phase shifts in on their phase modulators, and then Charlie, the photon will, it's only one photon, there are not 2 photons, huh? It's only one photon, you don't know which path it went, if this one or the other one, okay? And then, depending on the phases that they applied, the photon, when it arrives back here to the input-output beam splitter of the Sagnac interferometer, it can go one way or the other way to be detected at D0 or D1, okay? And actually, depending on the phases that Alice and Bob applied, this probability for detection, being detected here or here, can be 100% in one or the other, or 50%, okay? So what happens is that if both Alice and Bob, they use the same basis, 0 or pi, then the probability will be 100%. It will be 100% at D0 if they both applied 0 or both applied pi, or it will be 100% at D1 if the one applied 0 and the other one pi. Okay? If one applied 0 or pi and the other one pi over 2 and 3 pi over 2, then the probability is 50%. So how does the protocol work? Alice and Bob, Charlie sends like a number n of photons, okay? For each photon, he announces which detector clicked. So Alice, it's public. Which detector clicked is a public information. Alice and Bob will publicly also announce the bases that they used, but not the phase that they applied, okay? So with that, with those three information, Alice and Bob can know which phase shift the other one applied. And only they can do that. Only they can know that. Is that clear? Okay. So this is how it's going to work. In the free space link, we, in principle, will do the BB84, okay, first with only polarization, and then go to the alignment-free protocol. And in the future, we need to integrate this free space link with the, and this will be challenging, of course, but this is the high, how can I say, high target of the project, is to link the connection, the UFF-CBPF connection with the Sagnac loop, okay? So this is how this is a summary of the base of the protocol, okay? Alice choose the basis of within each basis she chooses a phase value. Also, Bob does the same, okay? And whenever they match the same basis, okay? Whenever they match the same basis, they will be sure that the detection announced by Charlie was obtained with 100% probability. So they can use the information announced by Charlie, and knowing his own phase shift, he can know, each one of them can know the other one's phase shift, okay? So the idea in this, the main idea was to have Charlie at the Catholic University, Alice at CBPF, and Bob at the Federal University of Rio de Janeiro. But another possibility that is now, maybe it will be faster because we have some technical problems in this link here. It's a very long link that passes through complicated areas of the city, okay? So another possibility is to use Alice, to move Alice to IME, Bob to PUC, and use CBPF as Charlie, okay? It's another possibility. So the main objectives of this project are those listed here, okay? We wish to establish a quantum key distribution network connecting 5 institutions, okay? 5 institutions. We want with that not only do the technical, how can I say, the technical work, but also develop new technologies, use it to develop new devices for quantum communication, promote a scientific exchange in the Rio de Janeiro area. So there are different groups that can work together. There are quantum memory, people working with quantum memory in one lab, going with different, working with quantum memory, with trapped ions in one lab, or trapped atoms. The other one with quantum memory in NV centers in the other lab. We have optical tweezer at Catholic University. So this would be very beautiful if we could, for example, generate one photon state in one lab, transmit through the network, register on the quantum memory in another lab. So this is the high target, okay? We want this network, once established, to serve as a test bed for new quantum technologies, or not only integrate the groups in the Rio de Janeiro area, but also integrate with other groups in the country and with foreigner groups that would like to test their technologies in the quantum Rio network, for example. No? So these are the participants of this. So there are many people, okay, but in each, I picked up one of each institution that is quite responsible for a given part of the project, okay? So I'm the coordinator of the project, and I also take care of the free space link and everything that is related to structured light in the research program of the network, okay? Guilherme Temporão is an engineer at Catholic University. He's a specialist in quantum key distribution, okay? He knows all the electronics and the optics and the quantum mechanics. So he has a very, very specific profile. It's not very common here in Brazil to have engineers with a good background in quantum mechanics, but Guilherme is a very important piece of the project, okay? Victor Andreso is also an engineer from the Military Institute, okay? He's also helping us a lot. He's working to make it viable, the connection with the Military Institute, and we are making very good progresses in that way. So Gabriel Aguilar is the researcher at the Rio de Janeiro Federal University, okay? Now, it's another problem is that he's moving to CBPF, so we don't know yet, we still don't know how it's going to work, okay? We have Ivan Oliveira at CBPF that works with us he's the coordinator of the project of the quantum memory in CBPF. Fernando Melo is a theorist that works in the security. He wants to investigate the security of the twin field protocol, okay? All the theoretical aspects of the security, okay? And Newton Alves is the guy who makes the connection between our project and the coordination of the Rio de Janeiro network, all that fiber link, everything. So, and whenever we need to ask them something, we talk to Newton Alves from CBPF. So, in conclusion of this series of lectures, okay, we talked about this non-separability, about structured light. How can we shape light in different ways, especially regarding its spatial profile, okay? We know that this degree of freedom, which is high dimensional and a very rich field for investigation, can be combined with polarization, and especially to produce non-separable structures that are non-separable already in classical optics, and that is a useful tool for quantum communication, okay? For example, to make alignment-free quantum cryptography, okay? So I would like just to advertise these books, okay? Claude Fabre he's now retired. He was a researcher, a very important researcher at Laboratoire Cassiler-Brossel in France, okay? And all the vision that I have about optics, quantum optics, photons, and the very basics is very influenced by the time I spent as a postdoc in their lab. He was there was a joint group between him and Elisabeth Jacobino, okay, and they both influenced me a lot in the way I see now quantum optics and the fundamentals of quantum optics, okay? And all his ideas about quantized modes, spatial modes, started in a Lesuche session, a Lesuche course back in 1995. It was a Lesuche school in quantum fluctuations, okay? I was there at that time. I was I had recently finished my PhD. I was a postdoc working at Laboratoire Cassel-Brossel. And afterwards, these courses became a quantum optics book, a very good book, which I strongly recommend, okay? It's really very good. And the quantization of the electromagnetic field is done in a more general way. It's beyond this naive picture of plane waves description, okay? It goes to more elaborate structures. And it's important because they are now easily realizable in the lab, okay? So with that, I thank you very much for your attention. Yeah, go ahead.
Could just briefly comment about why do you have to change the degrees of freedom you use in the fiber and in the freely? Like why change from polarization to phase?
Good question. So the point is that the fibers that were given to us or that were made available to us are regular fibers that have more than 30 years, okay? They were designed to single mode communication at 1550 wavelength, okay, nanometer wavelength, which is the telecom wavelength. So since it's single mode, so you see, when you talk about single mode, you go the opposite to structured light. A structured light, you need many modes. So with the fibers we have presently, we cannot use structured light inside the fiber. We can change the wavelength. We could go to other wavelength where the same fiber can be single mode in one wavelength, but multi-mode in another wavelength. But then, in these other wavelengths, the absorption is very large. Absorption, dispersion, and everything, and you just get spoiled. So this is the, how can I say, this is the simplest protocol that we can do with what was given to us. So in the future, if everything goes right, okay, if it works, we can apply for more money to buy, for example, hollow core fibers. Hollow core fibers are fibers that are empty inside. If they are large enough, they can accommodate several modes. We can talk about structured light inside the fiber without absorption, without dispersion, but needs money. It's very, very expensive, okay? Rafael. Thank you.
Two questions. One is about the twin field protocol. Because there you need a ring, right? But in the picture, I could not see this ring. So is there a ring there, like connecting? Because in one of the pictures, it looked more like a bipartite connection. So yeah, there in this picture.
That
Okay,
one.
so here you need a ring, right?
Well, the ring is the Sagnac. Okay, the ring is the Sagnac. So this is a beam splitter. It's a fiber beam splitter, okay? This is a beam splitter. So the Sagnac, it's the usual Sagnac interferometer. You have just two ports. One input, two input-output ports, okay?
But if optics that pass through lattice, they have to pass through both as well.
Yes.
And if you go to the other picture of the map, the next one,
The next one.
this picture of the map, yeah.
Okay, now I understand your point. Okay, thank you. Okay. So the point is that actually we asked, because of this architecture, we asked for a pair of fibers in each connection, okay? So actually the photons come here, go back, there, and come back.
So they have to travel
Longer. Yeah, but they go fast. They don't take the bus.
And the other question is about like entanglement. Would it be very difficult to just share entanglement?
You see, with the fiber, for the moment, with the fibers we have presently, it's the same answer that I gave to him. You know, with the fibers we have presently, no, I don't think so. I don't think so. So these are very old fibers, you know.
It would be nice to make a quantum teleportation.
Oh yeah, this is, well, you see, in my opinion, the most, how can I say, the probable quantum teleportation experiment is with the military institute. So we are talking with them about doing, sharing an entangled photon pair between CBPF and the Escola Superior de Guerra. Okay, I don't know how to translate that. And so the photons would be produced at the IME building, and one photon sent to the ESG, to the Escola Superior, and the other one to CBPF. And we wish to see the Bell inequality violation this way. Yes, please.
I actually live close to CBPF. I live close to CBPF.
Ah, you live close to the CBPF, so come visit us.
I visited, but I visit again. I know Ivan Oliveira.
Oh, Ivan Oliveira, okay, you know him, okay.
What do you use quantum error corrections for single photon state because it will provide a better protection for?
Yeah, well, for the moment,
What are your single photon states?
I'm sorry?
What are your single photon states?
So our single photon state will be attenuated laser. So we are going to buy, we have a laser at 1550.
No, Gaussian states or some Zelaquett, so I mean like the structure of all.
Yeah, they will be like Gaussian states, yeah, Gaussian states, yeah.
There are very good specific states for the best communication.
Mm-hmm. Good to know.
Quantum error corrections could be also used
Mm-hmm.
for protection of this.
Yeah, well, I think the specialist in quantum error correction would be Fernando. He has to, yeah, because he has been studying reservoirs and noise, open systems, and
How do you deal with quantum memory? Like you use repeaters?
so the quantum memory that when we talk about quantum memory here, we mean the experiment from Ivan, the NV Center. So they have vacancy NV Center in Diamond. So they have an experiment on that.
What is efficiency?
This I don't know. You have to ask Ivan. I don't know.
Normally it's not really big.
No, it's not very big.
But you're going to use quantum memory?
Well, for a single photon, yeah, one qubit, we will try to do that. Yes. Other questions? Thank you.